Welcome to our lectures on the microgrid and the control system. Today we shall talk about the microgrid system architectures and the AC interface. So, why AC interface? And that is also for the DC microgrid maybe. With the increasing demand for smart and the efficient load and rapid growth in the renewable energy sources, low voltage DC, that is LVDC power distribution systems can be suitable power grid for the many applications that we have discussed. In order to accommodate the new technologies such as this resources, that is RE is called the battery plus solar, it is called the electrical resources. The RES modifications in existing DC architectures are required to further enhance their flexibility and the controllability. Electrical power in DC system can be transmitted over, that is the advantage of it, 2-wire unipolar or the 3-wire bipolar system. That is, if you have a plus minus voltage, you require the 3-wire, and you require just a plus voltage, then you require the unipolar system. An interface, quite important, please understand, between the DC microgrid and the AC utility grid is very important. So, where you get power or send power from the DC, a DC microgrid get power or send power from the main grid. So, it absorbs power from main grid, or when it has got an energy surplus, it will send back the power to the main grid. So, essentially you require an AC to DC converter and vice versa. Increasing penetration of these resources such as PV wind turbine can offer possibility of transferring surplus power back to the grid, back to the AC grids from the DC side. That is quite phenomenal aspects. So, whosoever can pay, they can pay. So, once you have a energy surplus, like you may be a, maybe you can think of a winter vacations in the institutes like us, and where load has come down maybe 50%, then we become the net supplier and we sell power to the grid. So, that is possible. If it is a DC microgrid, then of course, you have to sell, you have to convert again DC to AC and sell power. And for this reasons, there are various AC to DC converter topologies which can be used in the AC DC microgrid interface. Even in some applications, multi parallel, we can do, if we have a power rating is more, then one path is not sufficient, you can have a, and also to give the redundancy, multi parallel AC to DC converters frequently used by sharing the common DC bus. Grid interface AC DC converter topologies for the DC microgrid. This is a bidirectional power flow converter. It can take power in a unity power factor from the grid with low THD, and that provides high quality sinusoidal current waveform. So, it does not inject any harmonics and other power quality issues. The system has, if it is a 2-level 3-phase 2-level inverter has been employed, then you can have the power switches such as IGBT or the MOSFETs. If you have a IGBT, the rating in and around of 10 to 100 kilowatt, or let us make it kVA, that more realistic. And if it is a MOSFET, it is below rather 5 below rather 10 kVA, and generally we prefer, though I have written here 10, above 5 kVA as IGBT instead of the MOSFET, and the control based on the suitable pulse width modulation technique. And we have studied that unipolar PWM. You can refer to my courses in advanced power electronics. So, different kind of modulation technique can be used. And in order to control the switching frequency ripple, a front side filter is required, and though generally it will be a PWM, the switching frequency is quite high, and thus filter size will be very small, and depending on this cutoff, if you have a L, then you have 20 dB cutoff, you have LC, you have 40 dB cutoff, if you have a LCL, you have 60 dB cutoff, and accordingly you can think of to have a different kind of configurations, and thus you can give a proper attenuations of your switching frequency. So, this is the one of the circuit diagram of active power filter. Assume that power is going from AC to DC side, and it is a grid, and you have a grid inductance, this is the leakage inductance may be coming for the transformer. Essentially the leakage stage of the transformer constitute the grid inductance. Thereafter, whatever the resistance of the total side has been put as a lump parameter as Rg, and thus you have a grid current. Since it is switching, you have a switching frequency ripples here, and that can be suppressed well by LCL filter. An LCL filter is a very common, and it can remove the high frequency current and clean the current at the grid side, and where at this point, and it is accepted within a power quality range. However, due to the stability issue of the converter, proper damping also required. Generally LCL filter will give you oscillations, and thus they are required to be damped out these oscillations, and it is become phenomenal when there is every switch is a transient. So, it has because its state will be changing. Let us consider the switch S1, once it is turned on, the corrector is then it try to increase the current. Similarly, once this is turned on, in negative cycle is try to increase the current. So, every switching is a transient, and thus there will be a huge problem if this filter is under damped. Please understand that. It is not that is the fluctuations of the load or source gives you the transient, and thus it is required to be actively damped. Of course, you can damp it, then there is a challenge because you can put a resistance here, and you will find that it has been damped out. But if you provide damping, you will find that your response or that whatever desired THD you want to have, that has also come down. So, that is a challenge, and there is many researchers working on it on the active damping of these LC filters, and you can refer a paper or you can mail me, I can cite the papers. The possible control techniques are definitely, that is I am going to say, the passive damping, that is what I was saying, by adding a resistors in series with a capacitor, which can affect the efficiency of the system. Of course, the losses occurred in the resistance is simply a loss, it is a heating, does not have any purpose. But apart from that, you also get higher THD if you have high value of the resistance, because time constant matters. Active damping, that is something like have to work with the control system by adding one extra variable in the control. So, you got a PI controller and we require to do something there, and adding the one extra state variable in the control method such as capacitor current in order to develop a visual resistors. So, previously, so what is the demerit of it? Essentially, you require extra sensor. So, cost will go up, and so once this information of the current sinking into the capacitor is available, so that becomes another state variable and you can control it, and thus it is called the actively control. So, either you put a resistance, that is passive control, so system become lossy and also performance is quite poor, but you can have active control, then you have to provide extra transducers. So, either of it, then whether the cost of the transducers, how many days you can pay off, this kind of economics will come into the picture. So, one of the major issue in the multi-parallel rectifier with a common desealing capacitor, and for example, in microgrid is a circulating current. That is also quite main problem. If there is a little mismatch between the pole voltage of this multi capacitor, there can be a circulating current in between, and we have to, and thus this circulating current will welcome the heating and thus it will welcome the losses. Circulating current depends on the topology of the rectifier and configuration of the overall system, that will show you in the next figure. As shown in the figure 2a, that is with the next slide, then two or more parallel rectifiers are connected to the DC network. The filter configuration can affect the configuration current due to the different rating. So, this is something we require to understand here. So, see that this is one converter, this is one gate, and you can have one rectifier and another rectifier in parallel, and you may have a loading and you may not have a loading here, but due to this loading and due to this capacitors value little mismatch also, what happen if you connect these 2 points to meet this loading, then there will be a different voltages across it, and thus there will be a circulating current within these 2 points A and B. So, that is what we say, the parallel connections of the two 3-phase rectifier different desealing filters configurations has been shown. Equivalent impedance loop in the positive DC bus legs and the negative DC bus legs can be referred here. So, this is a red portion of it is a positive DC bus, you got it you can model it here, that is your diode plus RD, there you got L and R, and thus you reach this point here. Similarly, from here you got the diode based rectifier RD and you reach it here, and then this point and this point can have a little voltage difference, thus current can circulate in between this point. Similarly, for the negative terminal, the parallel connections of the two 3-phase rectifier of different ratings, equivalent impedance loop in the positive DC bus legs and see the negative DC bus leg is been shown here, and in the figure 2a the two diodes rectifiers with the same desealing filters are considered. Even though topologies are same, the power rating can be different. So, current passing through it may be less because you are using a different diode, and that also may cause the potential difference in between these two. There is a very simple thing, here let us consider that it carry 100 ampere of current and it is carrying 50 ampere of current. Then voltage drop will be 1.4 into 100 ampere and voltage drop will be 1.4, that is 0.7 volt, 2 diode is conducting simultaneously if we assume. So, and this will be into 50. So, power loss and all those entities will be different in between this two rectifier. And that is what happens, the inductance value of the filters are determined according to the base impedance in per unit. Therefore, the inductance values are changed with respect to the power level as well. So, generally we say that inductance value is 5% or in a per unit value. So, once you change the different power handling capability, your design constraint also comes into the pictures. As we can refer in figure 2b and 2c, this one and this one, parallel legs, the positive or the negative DC links of the rectifier 1 and 2 are connected to the same terminal of phase and the VDC, that is something we require to see that. So, these are AA, BB, CC. Now, the major issue in this topology is that the DC current that is available in the output depends on the resistance of the DC link legs, mainly the diode and the DC link choke, while the ripple current depends on the inductance value. So, more the value of the inductance, it will smoothen the ripple quite well. Therefore, the current sharing significantly, therefore, the current sharing significantly depend on the quality and the tolerance of the component. So, that is something very important. So, once, because you know that the material comes into the picture. For example, the cheapest material for making the inductor is the ferrite, but it has a very fast roll off, that means the value of the inductance will drop very fast. You know that L equal to N phi by I, and if it saturates, then if you increase the value of the current, then L will come down. So, for this reason, that also depends on the quality of the component and its tolerance. So, you have loaded those inductors, then what will happen? If you have loaded that inductor with a better material like cool mu, it will have a different characteristics, and if you loaded that inductor made up by ferrite, you will find a very great roll off and value of the inductance will come up drastically from its 100% to the maybe the 30% value. So, those variations has to be considered in our design. The electronic transformer, that is one another important thing, it can be a matrix converter or indirect matrix converter, or the solid state transformer SST is considered as a key enabling technology from implementing the further electric distribution architectures such as smart grid, where you can have not only the voltage, but also the frequency control. And the application of SST has been already visualized in the microgrid in attractions and the data centers. So, in various kind of loading, so where you require a V by F control. So, it is directly AC to AC conversion, and in between, and it may have a fixed TTS DC link in case of the indirect matrix converter, and so that you can inject the real power and take out the DC power there, and generally this is the mode has been preferred in our microgrid. Now, grid interface electronic transformer for DC microgrid. It is quite interesting new topic. Dual haptic bridge or DAB based solid state transformer shows its application in DC microgrid, in which it can replace the existing passive transformer, which is made of, this is a dump transformer operated at the line frequency of 50 and 60 hertz, while providing the direct connections to the LVDC side. So, there it has got a flexibility. So, it can buck, it can boost, it can accommodate the change on frequency and control. It is an intelligent device. The SST concept enables equal functionality features that often AFE or active rectifier or active filters of the passive distribution transformer. I will show this figure in the next. So, this is the your high voltage AC transmissions, and generally what happen, you will have this active rectifier AFE link, we say it convert AC to DC. Thereafter you will have a DC to DC converter, generally it is of high frequency DC to DC converter, isolated high frequency DC to DC converter that provides you the galvanic isolations, and thereafter it has been an inverter. Purpose of this inverter, it can generate any voltage of the desired kind, and from there you can also take the low voltage output of DC. So, this flexibility is available, and also there is a possible, I first took the case of the B, and there is a possible of A, and you have a passive transformer, then generally it will be stepping down, and thus it is a very bulky, because you know that V equal to 4.44 FANB. So, if you have very high voltage rating, if your frequency is less in a transformer like 50 or 60 hertz, then ultimately N is something, it is the trans ratio. So, B and A has to be more. B is something, it is a material. So, you cannot have a drastically increase the size of the value of the B, and A is the window area of the transformer. So, you have to, that makes you the size. So, this transformer of course is employ a high frequency transformer, but that since it is a 50 hertz and this can be 10 kilohertz. So, the size of the transformer will be 200 times less, as simple as that. And in this case, let us, so what happened, we step it down from the high voltage and then you rectify it, and from there you take it the DC, it can be a control rectifier, and thereafter you can reconvert into the desired level of AC in case of the adjustable speed type. So, what we can say that the first one, that is active rectifier, this active front end we sometimes say, with the passive distribution transformer, this is a class A, and B is the SST topology with the in between high frequency DC link and the dual active bridge of the DC to DC converter. This is basically this one, we have to have a dual active bridge, because if you have a handling a bulk power, then resetting a flux is an issue. You can there are many DC to DC converter depending on the power rating. Of course, the least power rating is your flyback converter, that is your laptop charger. Thereafter, you have a forward converter. Thereafter, you couple them, the two forward converter, that becomes a push pull converter. Thereafter, you got a half bridge converter. Thereafter, you got a full bridge converter. This is a full bridge 3-phase converter. It is operated at a high frequency, and for this reason size become low, size become less. So, moreover SST topology integrates the DC to DC conversion stage dual active bridge topology shown in figure C, which provides the galvanic isolation and the voltage adsorption as shown in figure 3b. Now, typically SST includes the high frequency AC to DC power conversion, generates a high DC link voltage and then a high frequency DC to DC converter stage is required to regulate the DC bus voltage. This is the way it will work. Therefore, the SST is basically a 3 energy port system. So, that is the flexibility of it, unlike your passive transformer. The one port is interfaced with the high voltage AC and the other two ports are DC port and low voltage port of LVAC. And the 3 port characteristics of SST makes it suitable for the DC microgrid applications, where the input side connections of an AC or the grid or the distribution energy sources and the DC side of the PV, fuel cell and the battery system is shown in the figure 3b that we have shown here, the overall system. The SST based AC to DC conversion is a better power factor regulator, because we can have a control by the active rectifier. Also VAR compensation, we can employ the PQ technique for the VAR compensation, and also it can provide the galvanic isolation in the DC system. So, for this reason the research topic is totally shifted to the second topology of 3B. The overall SST based microgrid will be a more compact because of the high frequency, and with the penetration of the high bandwidth devices like silicon carbide, you will see that this power handling capability can go up to the megawatt level also, with the better functionality with an AC grid interface it is required. Thank you for your attention. I shall continue with the discussions with the different component of the DC microgrid in our next application, but before that I just wanted to conclude one thing, that this is the all this challenge here lying designing this transformer. So, that is something one has to be very good designer of the magnetics, and so and it has a turns ratio, and that will essentially will be almost same of that, but this will be the compact by 200 times. The area that it will have here and area it will have there is thus 200 times less. So, for this reason your compactness will come into the system. Thank you so much indeed.